Hello everyone, welcome. We are going to start week 11 today. Last week what we did, we introduced the displacement based method and then studied one such displacement based method. It is that is called slope deflection method, where a structure indeterminate for a given indeterminate structure, first we need to find out we need to get the primary structures which are kinematically determinate, and then calculate the fixed end moments, and then write the slope deflection equations, satisfy the equilibrium equation, and from the equilibrium equation we get the unknown displacements and rotations. And once we get the unknown displacement, again those unknown displacement can be substituted into the slope deflection equation to get the unknown internal forces, right. So, and then we demonstrated that method through some example. Okay, the method was efficient in any way, but you see, from the practical purpose, what we need is, as you remember in the very first week we said there are three aspects of design. One is safety, one is serviceability and economy, third one is economy. The safety says that in order to make a structure safe, we need to we need to know the internal forces in the member. Okay, see, strength of the member should be such that it can carry those internal forces. And then comes serviceability, which essentially tells you that the deflection in a particular structure should not be more than a certain limit. That's what the serviceability criteria we are concentrating in this course. So, safety is the first criteria. So, from practical point of view, it is the internal forces that we need first, than the displacements. Okay. But in slope deflection method, first we need to find out the displacement, and then from that displacement we could get the internal forces. Now, there is a method, but it would be easier, it would be better if we get without computing the displacement, if we can somehow get the internal forces, that would in some way that will reduce our effort, right. Anyway, displacements we have to find out, but without actually calculating displacement, if we can find out the internal forces. One such method is moment distribution method that we are going to start today. This is also known as Hardy-Cross method. Now, as the name suggests, the moment distribution method is the premise of the method is the distribution of moments. Okay. And what we are going to discuss now, how the moments, if we apply a moment in a given structure or a given joint, how the moments get distributed, and that distribution process constitute this method. Okay. So, let us first understand the concept of moment distribution method, and then we will apply those concepts to various examples. Okay. Now, you see, before we do that, some revision of stiffness coefficient that we already discussed, but since it is a very important ingredient in moment distribution method, let us revise that as well. Okay. So, if we take a propped cantilever beam AB, and then suppose a moment AB applied at A, it means that moment at A in a segment AB. Okay. Now, because of this moment, this structure may undergo a deformation like this. We take clockwise moment as positive, okay, for all the calculations, but when we draw the bending moment, we consider whether the moment is sagging or hogging moment. So, that is why all the moments are shown here or will be used as a clockwise moment. Okay. So, this is the and the corresponding rotation is considered as positive. Now, see, so this is the rotation at joint A, and joint B is fixed, therefore, there is no rotation, there is no the slope at joint B is 0. Now, because of this moment, there will be some moment generated at B as well, which is the support reaction at B, say that is MBA. So, MBA essentially moment at B in segment AB. Okay. Now, we have already seen this MBA, this moment is related to this rotation theta A as this, where 4 EI by L, this term is the stiffness term, right. And similarly, MBA is equal to which is the reaction at B is equal to, because of this moment applied at A, is 2 EI by L. Okay. That we have already seen. Now, So, now this we can write, this MAB we can write as MAB into k theta, where k is equal to 4EI by L, 4EI by this value, okay, and k is called stiffness of K is called absolute stiffness. Okay. Now, so if we apply a moment and then the rotation at that point is theta a, and that is represented by ma into k into theta, and where k is called the absolute stiffness. Okay. Or sometimes you can say stiffness. Now, next is we also seen that MBA is equal to this. So, therefore, MBA is equal to half of MAB. Okay. Now, this moment is called this MAB, the moment MAB, this moment is called carried over moment at B due to MAB. Means this when you apply a moment at one joint, and that will induce moment at another joint, and that moment is called carried over moment. Okay. So, now and then this MBA, we can write MBA as CAB into MAB. Okay. MAB is the moment at A, and CAB is the carried over factor. So, in this case carryover factor is half. Okay. So, carryover factor is essentially now CAB is equal to CAB is equal to, it tells you that it is MBA divided by MAB. Right. So, carryover factor tells you what fraction of moment gets transferred to the other joints when you apply a moment at any joint. Okay. So, these two is very important. One is this absolute, this stiffness term K, and the carryover factor, and also the concept of carried over moment. These three are very important, and we will see that they are the main ingredients of moment distribution method. Okay. Now, see one more example. It is now, suppose this initially the last example, this the support was fixed support. Now, let us make it hinge support. Both supports are hinge support. Okay. And now another moment MAB applied at theta a. Now, what is MAB? MAB is equal to, we have already seen it, MAB is equal to 3EI by L, and MBA is equal to 0, because it is now hinge support. Okay. Now, so MAB is equal to k into theta a, and k is equal to this value, and this is called this is absolute stiffness. Okay. And what is the carryover factor? Carryover factor will be 0, because when we apply a moment at this point, there will be no moment generated at B. Okay. So, carryover factor in this case is 0. Okay. Now, okay, another example, if we can see, suppose you take if we take a beam which is fixed support here, and we apply a moment at the fixed support. Okay. This is hinge, say for instance, this is hinge. Okay. Now, we apply a moment at the hinge this support. Now, this moment will not cause any induced moment at this point, and therefore, the carryover factor will be 0. So, even if it is fixed support, and if the moment is applied at the it is a fixed beam, the moment is applied at this point, and this will not induce a moment here, and therefore, what happens? Your the carryover factor will be 0. Okay. Now, next is moment distribution. Okay. Now, suppose consider a rigid frame which has 4 members, and then you apply, they are connected at O, and then one concentrated moment is applied at O. Okay. Now, all these the support conditions are at A and C it is fixed support, and at D and B it is hinge support. Okay. Now, what essentially we are going to see is, once we apply a moment at this joint, this some portion of this moment will get transferred to OC, some will go to OD, and some will go to OA, and some will go to OB. So, and total moments in all these members, if you sum them, the total moments is equal to, that has to be m0, that is the equilibrium condition at O. Now, what we are going to see here is in what basis this moment, the concentrated moment applied at O, will get distributed among the different connecting members. Different members are connected at O. Okay. Now, see, first suppose this is the deflected shape of this of the frame, where because of this load. Okay. Now, what we can do is, next is suppose take all these to let us derive a very general formulation. So, all these members, they have different length, they have different Young's modulus and different second moment of area. So, for Young's, and that is denoted by this subscript. Okay. So, all the members have different length, Young's modulus and second moment of area. Now, what compatibility, since it is a rigid frame, now what compatibility condition at O is, at this point O is, compatibility condition O says that all the rotation, all this rotation at this joint, rotation in all the members at this joint, they should be same. So, this theta A, theta OC, theta OD and theta OA, they all should be same, and suppose they are the value of this rotation is theta. Okay. That is the compatibility condition. Now, suppose now what we do is, we now take all these members that we have, that we take all these members separately, treat them separately. Okay. So, this is all separate members. Okay. Now, this is the concentrated moment applied at A, and the corresponding and the shear of OC is, suppose this one, MOC is the shear of OC. Similarly, MOD is the portion of the moment that gets transferred to OD, and similarly MOA is the moment in OA, and MOB is the moment in OB. Okay. Now, then there it is just, since we are only concentrating on the distribution of moment, in this diagram only the moments are shown, all the shear forces and axial forces, they are not shown in this diagram. Okay. Now, what is the equilibrium condition at O? The equilibrium condition at O says that all these moments, these MO, all these, the summation of all these contribution, all these shear, they should be equal to M0. Okay, that is the equilibrium condition at A. So, what we have two conditions here. One is compatibility condition, this one, and one is equilibrium condition, this one. Now, we are going to use both these condition, compatibility and equilibrium condition, to find out what would be the values of these moments. Moments in different members. Okay. Now, let us do that. You see, now this member, this can be treated as this one. Just now we have seen, for instance, say this one. Okay. Just now we have seen that if we apply, this is a fixed beam, and if we apply a moment like this, and then what is the corresponding if it deflects like this, then what is and it is theta. We have seen that this moment and this theta is how they are related, right. Similarly, we also have seen that if it is both end say hinge support, and then if you apply a moment like this, and suppose your deflection is like this, and this is theta, and how this moment and this theta is related. Okay, they are related through the stiffness, and the values of stiffness for this is the values of stiffness for this is this, and values of stiffness for this case is this. Okay. Now, take member AB, member OA, member OA. Member OA is essentially this is the idealization for member OA. So, the moment OA is related to theta OA as this, and this is the stiffness term. Suppose the stiffness is K of OA. Okay. Now, again this please take and theta, it is actually theta OA, but just in the previous slide we have seen there is all theta or theta OA, theta OD, theta OC and theta OB are same, and we assume that we assume the values of all these rotation is theta. So, that is why it is theta. Okay. Now, KOA is the stiffness at stiffness, it is due to the rotation at A, rotation at O in member OA. Okay. Now, so this is how the moment OA is related to theta and the stiffness. Now, similarly take member OB. Now, member OB, this joint is hinge joint, and this is the idealization of this is this. Okay. Now, therefore, we have seen it is the stiffness is 3 EI by L and OMOB 3 EI by L, and this is the corresponding stiffness. Similarly, for MOC and MOD, we can find out depending on their support condition. Now, in this, the concept is being demonstrated through only two support condition, hinge support and fixed support. The other ends are hinge and fixed support, but you can have different kinds of support at the other end, and based on the support condition, you have to choose get the stiffness coefficients. Okay. Now, then what we can do is now if we know the expression of all the moment in terms of their stiffnesses. Okay. Now, therefore, we can, if we take the ratio of all these moments, that can be written as the ratio of their corresponding stiffness. Okay. Now, if it is, then so just now we have seen this, all the ratio of their moments, they are essentially the ratio of their stiffnesses. Okay. Now, and then we have equilibrium condition this. Okay. So, this essentially we obtain this is from the compatibility condition, because we could obtain this relation because the theta for all these members theta is same. So, this is essentially the compatibility, the outcome of the compatibility condition at O, and then this is the equilibrium condition, right. Now, next if we use these two condition, this equation, so this is equation number 1 and this is equation number 2, then we can express MOA as this. Okay. So, this is the total, the summation of all the stiffnesses of all the members, and KOA is the stiffness of that particular member, and the M is the total applied moment. So, this is K0 by K. Okay. Now, if you remember we discussed absolute stiffness. This is the absolute stiffness, and this you can say this is the stiffness relative to the total stiffness. Okay. Now, similarly, so this thing we can do for this expression, what we have obtained for MOA, that we can obtain for other members as well. So, for other members also we can have similar these expressions for all the members. Okay. Now, so what this says? This says that moment, if we take a joint, if we take a rigid frame and apply a moment at any joint, then that moment will be distributed among the connecting members, and in what way they will distribute? This equation, this says that they will distribute in proportion to their stiffnesses. Okay. So, based on their stiffness, they will get distribute. Okay. Now, And then this is called, these factors are called distribution factors. Okay. Why they are called distribution factor? Because these factors essentially give you how they get, how the moments will get distributed. Okay. And the summation of this, all these factors should be equal to 1, which is obvious from their expression. Okay. So this is distribution factor. Okay. Now, next is let us once know what we have done, what we have learned so far. There are few terms we know now what is carryover moments. We also know what is carryover factor. We know what is absolute stiffness, and then we know what is distribution factor. Okay. Now what all these ingredients are now ready with us. Okay. Now we can start cooking. Now let us discuss what is moment distribution method, and all the terms that we have learned so far. The terms which have been introduced, those terms will be used in this method. Okay, great. Now let us demonstrate the method through an example. Okay. Now you see, this is an, if you compare this with slope deflection method, we get slope deflection method. There was no iteration in the slope deflection method, right? Once we get the equation, a system of equation, then it is a solution of this equation, and the theta that we get, that is the exact value with respect to the assumption that we made. Okay. Now, but moment distribution method, since we are bypassing that part, the calculation of displacement, directly we are going to evaluate the forces, internal forces. Now this method is an iterative method. You have to do it in an iterative manner. Okay. But that iteration is also very in a very standard way that iteration can be done, and that is we are going to demonstrate here. Consider this is a beam. Okay. It's a 2-span beam. End A and C are fixed, and 2 loading conditions on one at AB and one at B. It's a similar example. What we will be doing, you will see that almost we will be using similar example in order to demonstrate different methods. Slope deflection, moment distribution, then direct stiffness. We will be using more or less similar example. The reason behind using similar example is then you can really compare those methods, compare the values, you will get almost similar values, but the steps you can compare between the methods. Okay. Now, now the first take, there are 2 span here, span AB and span BC. Now let us separate these 2 span. Okay. Now because of this loading, okay, the span AB may deflect and span BC will deflect. Now take 2 spans separately. Okay. Now suppose this is span AB and this is span BC, and this angle is theta, and theta B, rotation at B, and this angle is also rotation at B to satisfy the compatibility condition. Okay. Now, so essentially we assume that deflected shape of the beam is something like this. Okay. Deflected shape of the beam, we assume something like this, and then we take AB separately and BC separately. The reason deflected shape is assumed, you may not get this deflected shape, but the reason why we took this deflected shape, because it is consistent with the sign convention that we are using for the moments. Okay. Now if your deflected shape is different, then you will get a different negative values. Okay. Now so this is 2 parts, part AB and part BC. Now you see, this is an idealization, these 2 idealization we have seen, that a propped cantilever beam, then a moment is applied at the propped end. Okay. Now for this, what we know, that KBA is equal to this 4 EI by L. Now assume EI is constant for both the cases. It is also EI, it is EI and EI. EI is constant for both the cases. Okay. Then what is K, this the absolute stiffness for this at joint B, this become this. And similarly for this member, Similarly, for this is an idealization of again C. So, KBC is again this means, it means that if you apply the moment at B, then and there is a rotation at B, then this moment and this rotation they are related to their stiffness, and that stiffness is this. And similarly, if you apply moment at BC, it will undergo rotation like this, and this moment and this rotation will be related with the stiffness coefficient KBC, right. Now, then what is the carryover factor? Now, what is the distribution factor? Distribution factor, we have seen that distribution factor for this will be KBA plus the total stiffness, and this becomes half here, and similarly distribution factor for this will be half for this member as well. And then what is the carryover factor? Carryover factor will be half. Carryover factor is, if we apply the MBA moment here, the moment generated at the other end is MAB. Similarly, if it is MBC, moment generated at the other end is MCB, and MCB will be half of this, MAB will be half of BA. That is carryover factor. So, we have already discussed this. Okay. So, we have already discussed carryover factor, then we have already discussed distribution factor, and we have already discussed what is stiffness. As I said, these three, these are the ingredients of this method. So, this is how they are required to use this method. Okay. Next is let us do all these steps. Okay. First is the step 1 is, it is very similar to slope deflection method. Step 1 is the essence of the whether we apply a displacement method or moment distribution method, any method, they all are displacement based method, and the essence of displacement based method, the general steps in displacement based method will remain same, and how we are doing that step, depending on that we have different methods. Here those steps are being performed iteratively. The first step, if you remember, we discussed in the previous last week, that we get the primary structure which is statically determined, which are kinematically determinate, right. And how do we get that primary structure? We know what is the kinematic indeterminacy of the problem, and then we need to constrain that corresponding degrees of freedom. So, therefore, all the joints we have to make fixed joint. So, this become fixed joint. So, this is a kinematically determinate structure, or this is the primary structure. Okay. Now, primary structure, we have to, it is subjected to the external load, and because of this external load we will be having some moments at the end, and those moments are called fixed end moment that we discussed in the last week. So, what will be the fixed end moments for this? Fixed end moment for this will be, in this case it is minus 62.5, and these are the fixed end moments. Okay. And we know how to calculate fixed end moments. For this case it will be WH square by WH square by 12. For in this case also we know the value. For different loading conditions we know how to calculate fixed end moments. So, this is the fixed end moments, right. For this, the fixed end moments will be actually hogging moment, but here when we write the moment, write the sign of the moment, we write based on whether the moment is clockwise or anti-clockwise. Clockwise moments are positive. Okay. So, we show all the moments as clockwise moment, but when we write the value for anti-clockwise, it becomes negative. Okay. So, these are the fixed end moments. So, once we know the moments, now you see what is the there is no external moment here, right. If there is no external moment here, then what happens? The member MBA, if you remember slope deflection equation, we wrote that MBA plus MBC, that has to be 0, isn't it? That is the equilibrium condition at B. Now, let us see whether that equilibrium condition is satisfied or not. Now, here this equilibrium condition is not satisfied. So, there is some unbalanced moment, right. Now, step 2 is calculate the unbalanced moment. Now, what is the unbalanced moment here? Unbalanced moment at this joint will be this plus this, and in this case it is minus 0.95. Now, this unbalanced moment needs to be made 0, right, because because there is no externally concentrated moment here. So moment at B in both the segment, they should cancel each other. Now next step is we have to make it 0. How do I make it 0? Just by if we apply, and if it is minus point, if we apply an additional moment here which is 0.95, suppose fictitious, you apply an additional moment which will balance each other, right? Now then this, the equilibrium is satisfied. We are going to do that. So then balancing moment, how do I balance the moment? We apply and 0.95 moment here. So it is unbalanced moment. In order to balance that, same value but in opposite direction we need to apply. Now when we apply this moment at this joint, they will, that moment will, it is the moment applied at the joint, but what we are interested now in, how much of this moment will get transferred to this member and how much of this moment will get transferred to this member. And just now we discussed moments will get transferred based on the distribution factor, based on the their stiffnesses. And what is the distribution factor for this case? We just now, we have seen the distribution factor is half and half. So half of this moment, that 0.95, that will get transferred to this member, and half of this moment will get transferred to this member. So the next step is distribution of the balancing moment. So this is the balancing moment. Now that moment needs to be distributed. So distribute that moment. This half of this moment goes here and half of this moments goes to this member. Since this is positive, all the moments are positive. Okay. Now then once this moments goes here, then this will generate, okay, this will generate some carried over moment at this point, and this will generate some carried over moment at this point, right? Now, so 0.475 you are applying on this, you are essentially what we are doing, we are this is a beam, this is a beam, this is a beam, and we are applying 0.475, and this 0.475, this is a balancing moment. That moment will generate some carried over moment here. Okay, and what is the carryover factor? Just now we have seen, for this carryover factor is half. Similarly for this member. So let us do that. So next step is carried over the distributed moment. So this is the distributed moment that will carry over to the other end. And what is the carried over moment? Carried over moment will be, since the distribution carryover factor is half of this moment will go there, and similarly half of this moment will go there. Okay. Now step 6 is, then once it goes there, let us see what is the presence, what is the status now. The status is now, let's see what is the moment, total moment we have at this joint, and at this joint. So step 6 is, let us, so this is carryover factor, okay, this is carryover through carryover factor. Step 6 is step 1, so this step plus step 4, and then step 5, okay. So you sum them. So what is the total moment now we have at different joint A, joint B and joint C. Now total moment will be, so at this point the total moment will be, so you sum them, it is this value, and then at this point the total moment is this value, and at this point the total moment is this, and at this point the total moment is this. Now this is a complete cycle. Okay. Now after this cycle, let us see what is the present status. So this is essentially now this step is essentially for the next cycle, this step is essentially next cycle, this step. We started with this when we saw that there is an unbalanced moment at this joint, and then we balance this unbalanced moment and correspondingly distributed and carried over moments we have. Now the after step 6, let us see what is the present status, whether we have any unbalanced moment or not, right? Now if we have any unbalanced moment, then again we have to do the similar step 1 to 5 on this. Okay. Now again, obviously I chose a problem where we get balancing moment, where we get perfectly balanced moment after the end of step 1, because the objective here to demonstrate these steps. We will be doing some example where even after one cycle we will see that there are some unbalanced moment, and we have to repeat the cycle. We have to get it the balanced or equilibrium position, we have to do the iteration, repeat the iteration until we get the equilibrium position. Now it is now in equilibrium position. You see, this is positive 6.725, this is negative 6.725, and they can balance each other. So this is the final status, at least for this problem. But it may so happen that after one cycle you may not get the equilibrium stage, and in that case you need to repeat the process. That will be demonstrated through some example. Now let us for this, now in general, for this example I showed you in a very with all these beams and supports drawn, but when you actually do it, that can be do it in a tabular form. We will demonstrate that. So this is the same thing, but written in a tabular form. So this is one axis. This is, we started with this where we have an unbalanced, these are all fixed end moments where we have an unbalanced moment at this point. Then we distributed the moment and their distributed moments were carried over to other end, and then we sum them, this and this, and then this and this, and this and this, and this is the final status. So this is complete cycle, and we were lucky in this case that after one cycle we got the equilibrium stage. Now finally, this is the final moments at different joints. Now if you have to draw the bending moment diagram, let us draw the bending moment diagram. The bending moment diagram will be bending moment due to the external load, and then plus bending moment due to this moments at different joints. So because of the external load, this is the moment on AB is this, and this value is WL square by 8, we know this, and because of the external load in BC, this is the bending moment diagram for BC. This is 12.5. Now on this we need to superpose the bending moment for this, for the joint at the joints, and this bending moment will be for this joint, for this member it is 6.012 and the 6.725, and then for this it is 6.725 and 5.03538. But when we draw the bending moment diagram, please make sure do not draw the bending moment diagram based on clockwise or anti-clockwise moment. See whether the moment is hogging moment or sagging moment, and that is the sign convention we use for bending moment diagram. And then this is the bending moment, the red lines, that is the bending moments in this. So these are the positive moments, and these are the negative moments. So this is the final solution of this problem. Okay. Now what we do next is this, the idea, the objective of today's class has been to just demonstrate, to introduce the moment distribution method and to introduce the steps involved in moment distribution methods. That will be demonstrated through some examples in the subsequent classes. Okay. So next class we will see, next class onwards we will see some examples where indeterminate structures are solved, are analyzed using moment distribution method. So in the next class, thank you.